All right, this is going to be our last section of notes. We are testing on Wednesday this week. So tomorrow we will be doing a review. If you know that you're not going to be here tomorrow, it is a packet, so get it from me today. Okay? What's the matter? You're allowed to talk while we're recording. It's a normal class. It's okay. All right. So we're looking at functions and modeling them based on formulas, graphs, verbal descriptions, and data. We've been talking about what makes something a function, vertical line test, all that stuff, right? So today is focused more on can we write those functions. All right, the first one says we're going to form functions from a formula. What is the formula for the area of a circle? What comes to mind? Area equals, whoops, area equals pi r squared? Okay, so what we've just done there is we've written area in terms of its radius. We've written a function or a formula in terms of r. Okay, so if we knew the radii of a whole bunch of circles, we could figure out their area pretty easily. The second two parts say, what if we know the diameter or the circumference? Can we rewrite that formula? So instead of it being in terms of r, we want it to be in terms of d. What is the relationship between r and d?
R is half of D.
So we could take this and substitute it in. All right, let's do that. So area is going to be pi times 1/2 d squared. Instead of radius squared, we're going to put in 1/2 d and square it. What do we get if we square 1/2?
1/4.
Okay, so simplifying this, we would have 1/4 pi times d squared. And now we have area in terms of diameter. Okay. Our last one is we want to convert it into being in terms of circumference. Now you can take either of the first two formulas that we have. You can convert radius into circumference, or you can convert diameter into circumference. It doesn't matter. If we go with this diameter version, what is the formula that we have for circumference? Circumference equals, if we have it in terms of diameter. I heard 2 pi r, but in terms of diameter, it would be pi d, pi times diameter. So what would diameter be? Circumference, yes, circumference divided by pi. So now we're going to plug that in. You want some pi now? Okay. Area equals, our formula was 1/4 pi diameter squared. So 1/4 pi, and then instead of diameter, we're going to use circumference divided by pi. But diameter was getting squared, so c over pi has to get squared. Which just means we square circumference and we square pi. Okay, simplifying this. We have 1/4 pi times c squared over pi squared. Can we reduce out some of that pi? You hope so? You're going to eat it for us? Okay. What do we have left after Jared eats the pie? This pi goes away and then one of these? Yes? So we have c squared divided by pi. Now, you can simplify that. You can just write that as c squared over 4 pi. Clean that up a little bit. All right, so what we've done is we've taken that basic area formula and we've written it in terms of several different variables, in terms of radius, in terms of diameter, in terms of circumference. Okay, so if you were given the circumference of a circle, you could easily calculate the diameter by plugging it into this last formula, instead of having to find diameter or diameter or radius and then calculate area. Okay. Questions on that first one? All right, our second example. You've done this type of question in Algebra 2. We're trying to maximize the volume of a box. So we are given that we have a square of side x inches that's being cut out of each corner. So this little square here is going to be an x by x square. The original cardboard was 8 inches by 15 inches. And we're going to cut these little square corners out and then fold along the dotted lines to make an open box. Okay? So their first question is to write the volume of the box as a function of x. That means we want some kind of formula where volume is in terms of x. What do we need to know to find volume? Length times width times height. So let's think about when we fold this up to make a box, what are my dimensions? All right. I started out from here to here was x inches. But I'm cutting off how much on each edge? I'm cutting off x inches on each side. So instead of it being 8 inches, now it's going to be what? Yes, 8 minus 2x. So one of the sides of my box will have dimension 8 minus 2x. Now the same thing is happening on the other dimension. We started with 15 inches and we're taking x off of each end. So that side would be 15 minus 2x. And if we fold along the dotted lines, what is my height? Just an x. Yep. Okay, so our volume formula then is those three things all multiplied together. And we can just leave them like this. We don't have to actually FOIL it all out. Okay, that's the formula for volume in terms of x for this particular box. Okay. Part B says find the domain of the volume as a function of x. Note that the model imposes restrictions on x. If I just was looking at this formula and had no context around it, there was no word problem describing what all that stuff was, there are no domain restrictions. I could put any number in there for x. But because I know that x stands for this corner length that I'm cutting out, there are restrictions on it. Can x be negative? No. Can x be 0? And that's kind of a gray line. Some books will say, yes, we know the concept of 0. We can say we have a box that has no volume. All right, it would be flat. It wouldn't have a height. All right, so some books, and your book in particular, lets it be equal to 0. All right, other people, I know last year the Algebra 2 book argued that you can't have a box with no volume. So they had it being strictly greater than 0. All right, for our case, we are going to say we could have a 0 volume. So my domain restrictions. X has to be non-negative, 0 or higher. But that's true for all the sides, right? They can't be negative. So that means that 8 minus 2x also can't be negative. And 15 minus 2x can't be negative. All right, so solving those two inequalities. We're going to add the 2x over, divide by 2. What does that tell me about my x value? So far we know that x has to be greater than or equal to 0, but this one says x also has to be, careful, x has to be less than or equal to 4. So they're saying that side that I'm cutting out, that little corner, can be somewhere between 0 and 4 inches. Okay? What would we get over here on this third side? X would have to be less than or equal to 7.5. Now, if this restriction says that x can't be bigger than a 4, then this one doesn't matter. There's no way I can go up to 7.5. If you think about it in terms of our picture, could we cut off 7.5 here and 7.5 here if we only had 8 inches to start with? No, wouldn't make sense. So could we cut off 4 from either end? That would be the max, right, that we could take off, because then we're out of side. All right, so our domain here is going to go from 0 to 4. And again, some books would argue that these would be rounded brackets because you can't actually have it all disappear. All right, now it says graph v as a function of x over this domain. So you're going to grab your calculators and you're going to put this in as your window for x. Okay, that means when we graph this, you're going from 0 to 4 for x. What shape would this be? We can type it in unmultiplied just like we have right here. Okay, we can type it in just like that. But what would it have been if we multiplied, just look at your x. You have an x times negative 2x times negative 2x. What do we get? We'd have a 4x cubed as our first term. So it's a cubic graph, right, with a positive leading coefficient. So it's going to start low and twist up. Yes? We said it could equal 0 at 0 and 4. So we're going to hit here and here. We'd also hit out here at 7.5, but remember we said that's not in our domain. So we have this cubic graph that's going to do something like this, but we're going to ignore that other part. Okay, we're only looking from 0 to 4. Play around with the window for y. See how high you need to make it in order to see that peak. When somebody finds it, let me know. Anybody have a good window? What'd you set it for? 100? All right, so set your y values to go from 0 to 100. You should see a nice peak. Yes? Okay. Now it says, use the maximum finder on your grapher to determine what that maximum value would be. So we're going to go in and say we want to find a max. We need to set a left and right bound. Remember doing that? Saying look in between these? All right, take a minute and do that. What'd you get? 90.741. Agree, disagree? Okay, what kind of units would we put on there? What were our sides being measured in? Inches, so volume would be inches cubed. Yep. Okay, and then the last question says, what size should that x be to give us that maximum volume? What was your x coordinate at that highest point? 1 point, give me 3 decimals. 1.667. So if we cut off 1.667, or about 1 2/3 inches from each side, and folded it up, that would give us the maximum volume for that box. Questions on that one? All right, question 3. We're looking at forming a function from a graph. It says, a small satellite dish is packaged with a cardboard cylinder for protection. The parabolic dish is 24 inches in diameter and 6 inches deep, and the diameter of the cardboard cylinder is 12 inches. So this here is 12. How tall must the cylinder be to fit in the middle of the dish and be flush with the top of the dish? Okay, so we have this cylinder. It would be open on the red side here that I just marked, open on the top, going down. Okay. and they're asking for what is this length. Now, this is a real typical kind of conic section problem, which we'll get to later this year when we start looking at hyperbolas and ellipses and all of those. The key to setting this up is to think of it being on a coordinate plane. All right, we have a parabola. This shape right here, there's going to be some kind of quadratic equation for that parabola. And if we can find that equation, we can answer this question. So we're going to think of moving that parabola and putting the vertex here at the origin. And notice that the parabola here, they're saying that that equation keeps going. But remember, our dish is only 6 inches high. So we are going to cut it off here. Does that make sense? Okay. Now, think about it. If we put the vertex at the origin, and it's 24 from here to here, then it's going to be 12 on this side and 12 on that side. Yes? Does that make sense? We're just splitting it down the middle. So this point is given with coordinates 12, 6. We went 12 to the right, and because it's 6 inches deep, we went up 6 to have that corner. So that blue dot is this point right here. Okay? Now, we can do the same on the other because it's symmetric. This would be 12, negative 6. All right? It's a right side up parabola. So we have y equals some constant times x squared. We haven't shifted it left, right, up, down at all. Vertex is at the origin. Gives us a nice basic equation. In both cases, whether we put in a positive 12 or we put in a negative 12, we got a y value of 6 out. Okay, so I'm going to put a 12 or a negative 12 in here for x, and I'm going to figure out what kind of constant I need that would give me a 6 for an answer. Well, what's 12 squared? So if we divide over 144, we've got 6 divided by 144 equals our constant. Can we reduce that at all? 1 over 24. Okay. So my equation is going to be y equals 1 over 24 times x squared. That 1 over 24 just squashes my parabola, right? It's a vertical compression, so it's kind of a flatter looking parabola. All right. Now, the question they asked us was how big is this dimension? Can we find this point on our curve? We know an equation for the curve. Yes? And we know that if this was 12 across here, and we split it, we centered it around the y-axis, then we're only going over 6 and down to that point. Okay? So we know the x-coordinate is 6. We're going to figure out the y-coordinate of that point. It's on my curve, so it has to fit this equation. So I'm going to put a 6 in here. So 6 squared would be 36 divided by 24. What does that give us? Three halves. Yep, or 1.5. So it has coordinates 6, 1.5. So that means that this space right here, we went to the right 6 and we went up 1.5 to get to my corner. Okay? So if I went up 1.5 and I know the total height of that parabola, or that satellite dish is 6, what's left for the cardboard part? All right. So we would want to make that cylinder 4.5 inches tall, and then it would sit in there and be flush with the top of the satellite dish. Okay? Questions on that one? All right. The next topic was, can we form a function just from a verbal description? We don't see a picture or anything, just have a verbal description. It says grain is leaking through a hole in a storage bin at a constant rate of 8 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. If the cone is 1 foot tall now, how tall will it be in 1 hour? The statement here that the height remains equal to the radius is going to allow us to simplify our volume formula. Instead of having volume in terms of radius and height, we're told that radius equals height. So I can replace my r with just an h, and my formula becomes 1/3 pi h cubed. So instead of r squared times h, we have h squared times h, or h cubed. Now, I chose to leave h in there because it asked me to find the height, right? So we want it in terms of h. Okay, so we're going to start out figuring out what is the height and volume right now, and what is the height and volume after an hour. So current height. What did they tell us the current height of the cone is? It's 1 foot. But our rate of change here is given in terms of cubic inches per minute. So can we think of that in inches instead of feet? Okay, 1 foot is the same as 12 inches. Okay, so can we calculate the current volume? We know a height, we can plug it in there. So volume equals 1/3 times pi times 12 cubed. Let's leave pi in there. Let's just take 1/3 times 12 cubed. What do you get? What are we getting? Jared. Thank you. Now, that means our volume is 576 times pi, and that would be inches cubed. All right, so we know the current stuff. What's the current height? What's the current volume? Now we have to look at what happens during that hour. Okay, how does volume change during that 1 hour? They told us it's going up by 8 cubic inches per minute. And how many minutes in an hour? I know that was a tough question, wasn't it? Took everybody a minute to think there. Okay, 8 times 60 is 480. So in an hour, we're gaining 480 cubic inches of volume. So what will our volume be in 1 hour? We had 576 times pi cubic inches, right? That was our starting point. And then we're gaining 480 more cubic inches. That's going to be our new volume. And now go back to your formula. If you know volume, can you find height? All right. So we've got 1/3 pi h cubed equals all of this. All right. How am I going to get rid of the 1/3 over here if I'm trying to solve for h? Okay, so I'm going to leave this all like it is. I'm not going to convert to a decimal yet. We're going to take our current volume, we're going to multiply it by 3 to get rid of the 1/3. What are we going to do with pi? Divide it off. Okay, that gives me h cubed left. And how do I get rid of the cube? Cube root it. So with your calculators, you're going to take the cube root of all of this. All right, check your work. I'm getting 12.979. Yes? Okay. So what was the height an hour ago? It was 12 inches, right? So during that hour, we gained about an inch, just a little under an inch in height. Okay. This was the question they asked, though. What is the new height of the cone? Which means the radius changed by an extra 0.979 inches as well. Diameter would increase by about 2 inches. Okay. All right, question 5. It says, let the units work for you. We're going to use some dimensional analysis where we use the units and help cancel them out to help us convert this. It says, how many rotations does a 15-inch radius tire make per second? So rotations per second on a sport utility vehicle that's traveling 70 miles per hour. So we know the speed, 70 miles per hour. We want to convert that to rotations per second. Okay? So we have miles per hour. We want to convert to rotations per second. So we need to convert miles into rotations. We need to convert hours into seconds. The first thing we're going to do is figure out what do they mean by a rotation. So if you take your tire, right, and one spot on it, if you make one rotation, what are we talking about? What is that geometrically? The circumference. Okay, so one rotation is really the circumference of your tire. So what is the circumference? What was our formula for that? Circumference equals 2 pi r. And r was 15 inches. So we get a rotation of 30 pi inches. Okay, every time the tire rotates, it's covering 30 pi, around 90 inches. Okay. All right, so let's do our conversion. We are starting with 70 miles per hour. Let's start just by converting time. We want to convert hours into seconds. So convert hours to minutes. 1 hour is the same as 60 minutes, and 1 minute is the same as 60 seconds. So what we've done so far is we've gotten rid of minutes and hours. Now we have miles per second. So our time is in the right units. How do we convert miles into rotations? Okay, so we can start out converting feet. So 5,280 feet per mile. Okay, so miles is gone. How do we convert feet into inches? 12 inches in every foot. And then how do we convert inches into rotations? One rotation is equivalent to, careful, 30 pi inches. Whoops. All right, so we can convert or cancel inches, and now we have it in rotations per second. So now it's just a matter of typing all that in your calculator. Be careful here. It's real common for students to say, I'm going to divide by 30 and then multiply by pi, but multiplying by pi makes it as if the pi is on top. So put this in parentheses. All right. You should be getting 13.072 rotations per second. We good with that? All right, we have one more example to look at. This is forming functions from data. All right, so we're going to use your calculator to do some regression. All right, it says constructing a function from data. Given a set of data points of the form xy, to construct a formula that approximates y as a function of x. Your first step would be to make a scatter plot. Your points do not have to pass the vertical line test. They can be wherever. All right, we're just using that scatter plot to help us think of the shape that we need. Okay, so determine from the shape of the plot whether the points seem to follow the graph of a familiar type of function. Does it look linear? Does it look like a parabola, quadratic? Does it look like it's an exponential growth kind of curve? Is it looking like a sine curve? All right, you can tell from the shape what kind of regression you need to do. Okay, so we are going to let our calculator then actually come up with the equation for it. Our table here records the low and high daily temperatures observed on September 9th of 1999 in 20 major American cities. Find a function that approximates the high temperature y as a function of the low temperature x. And then use this function to predict the high temperature for the day for Madison, Wisconsin, given that the low temperature was 46. So we have 20 cities here in two columns. We have low and high temperatures for each one. We are going to put x's as our low and y's as our high, which means we want to put list 1 as the low temperatures and list 2 as the high temperatures. All right, we'll pause the video. You guys go ahead and enter that. Go under Stat Edit, all right, and get your two lists in there. Okay, so once your data is in there, how do we see a scatter plot of it? What do we have to do? Second y equals key. All right, you want to turn your stat plot on. Okay. And you want to make sure that you have list 1 and list 2 as your x and y lists. Okay. All right, go ahead and graph a scatter plot. We're going to use this window that they've suggested here. Go 45 to 90 for x's and 60 to 115 for y's. But keep in mind that you won't always be told what window to use. You can go to your table of values and say, what is the lowest low and what's the highest low value? In other words, for x's, what's the smallest and largest I need to get to? And then do the same thing with your y values. Okay? So take a minute and go ahead and set your window and graph it. What shape does it look like? Does it appear linear? Does it appear like a parabola? Does it appear like a cubic twist? There is positive correlation, okay? It looks fairly linear, yes? The points seem to be moving up and to the right? Okay. So we are going to do a linear regression. All right, so you're going to go to Stat, Calc. Number 4 should say linear regression. All right, so on our calculators, we're going Stat, Calc, number 4. I'm going to tell it that I am using list 1 for x's and list 2 for y's. You guys with the newer calculators, it should say x list and y list. Okay, and then go to where it says store equation and type in variables. Go over to y variables and then choose function and y1. And what that's going to do when I hit enter here, it's going to calculate the line of best fit, but it's also going to dump it into my y equals screen so that I don't have to type it all. Okay, so in the store section, we did variables, that key. Then we went over to y variables, and then we chose function and y1, the first choice on each. Okay, hit enter. And it gives me this big long equation. All right, we've got y equals 0.96989 x plus 23.0148. Okay, now if you go to y equals, they took the whole thing. They dumped the whole equation in there, all the decimals, everything. So it's going to be more precise. When you hit graph, it should draw that line through your points. All right, so you should see a line coming up through there. Now, not all your points are fitting it. That's okay. It's considered a line of best fit. They took all the data and said, what's the best line I can fit to this data? And now we can use that to find the temperature when our low was 46. That was the second question they said. What would the temperature be in that town if the low was 46? So you can either type it in by hand, or you can go to your table and look at what you get for 46. All right, so we are getting a y value of 67.63. And the actual high temperature of that day for that city was 67. So our formula is pretty accurate for that. Okay, just a couple comments. The last few pages here of notes are just some things we want to talk through. It says professional statisticians would be quick to point out that this function should not be trusted as a model for all cities, despite the fairly successful prediction for Madison. For example, if we used that formula to predict San Francisco's high temperature, putting in a low of 54 and a high of 60, or we get a high of 64, but it's off by 11 degrees. It was actually 11 degrees warmer that day. So what they're trying to point out, the effectiveness of a data-based model is highly dependent on the number of data points and the way they were selected. For us, when I ask you to construct an equation based on data, we are going to look at how well it fits that particular data. We're not going to look at how well it fits the overall population. Okay? So just that data. The chart here just shows you some of the types of functions that we're going to be looking at this year. and what chapter they come in. Our last piece says these graphs are only examples, as they can vary in shape and orientation. For example, any curve could appear upside down. The grapher uses various strategies to fit these curves to the data, most of them based on combining function composition with linear regression. We're going to just let the calculator do all that work for us. Depending on the regression type, the grapher may display a number r called the correlation coefficient, or a number r squared called the coefficient of determination. In either case, a useful rule of thumb is that the closer the absolute value of this number is to 1, the better the curve fits the data. So looking at your screen, just quit out of your table for a second, and it'll go back to that screen. Notice the R value that we had, 0.89857, all right? That's fairly close to 1, but it's not perfect. And when we looked at the graph, you saw the line, and not all the dots were on the line, right? So I would say it's fairly linear, but not perfect. Now, if you did not have an R value show up when you did this, you can turn those diagnostics on. You go under Catalog, which is second 0, and scroll down to Diagnostics On. You have to hit Enter twice for it to turn it on and finish the process. Okay? All right. If you need help with that, let me know. Here is your assignment.